Welcome to the Game Changers seminar. Good afternoon for those joining me from Europe, and good morning for those joined from the US, or a late good evening for those who join us from Asia. We have a talk today about planetary magnetic fields, and planetary magnetic fields are intrinsic properties of the planets, and there are an intellectual challenge to explain, how they come about. I mean, there's been a long history of literature and thoughts about how we generate dynamos inside planets in the cores, and we have one of the leading dynamo theorists with us, Sabine Stanley, who will present us the latest on that. Now, Sabine is the Morton Blaustein Chair and Bloomberg Distinguished Professor in the Department of Earth and Planetary Sciences at Johns Hopkins in Baltimore. Her research, of course, goes to understanding the magnetic fields of planets, but she does more. She tries to understand the interior structure and the state of planets, and how you can use the magnetic data to learn about that. And she covers dynamo theory, but for terrestrial planets, but she's also much involved in understanding the magnetic fields of giant planets as well as of exoplanets. And therefore, we're looking very much forward to your talk, Sabine. Just let me say that we're a little pressed in time, so we will be stopping a little after maybe the hour. And as always, you have two ways of asking questions after Sabine's talk. You can raise your hand using the feature of Zoom, or you write in the chat, and then I will read the question to Sabine and the audience. And with that, Sabine, the floor is yours. I'm looking very much forward to your talk.
Okay, thank you very much, Tillman, first of all, for the invitation to come speak with all of you today, and thank you all for joining. So we're going to be talking about planetary magnetic fields today. Let's go. So I think if we're going to talk about magnetic fields, an obvious question to start with is why bother studying magnetic fields? And here's where I really have to admit that electricity and magnetism was my worst subject in undergrad, right? And yet here I am studying them, so there must be a reason. And really, we have to keep in mind that many planets and even a couple of moons in our solar system have or had intrinsic magnetic fields in their history. And so those magnetic fields, aside from just being really cool to study, you get to look at cool pictures like this, and it's a really interesting fluid dynamics problem that you can apply sort of the mechanisms and mechanistics of chaos theory and so forth. So it's really just interesting from an academic perspective. But if we're trying to think about what we can actually learn about planets by studying their magnetic fields really provide info on two really hard to reach places. Okay, so here's the first place, a planet's deep interior. Magnetic fields, because they're generated by dynamo action deep inside the planets, and because we can see them readily with spacecraft or at the surface with observational equipment, they act as a probe of things that are happening very deep in the planet. And so we can learn about the deep interiors of planets. Now, what's the other place that magnetic fields help us study? And that's basically the planet's deep past. Okay, magnetic fields, because they're frozen into crustal rocks on the terrestrial planets, as those rocks forms, they really give us a record of what the dynamo was like in the past on planets. And that means a record of what the planet's thermal evolution was like and the conditions were like. And really, I think we have to remember that some of the fundamental features that we consider about Earth right now, for example, plate tectonics, that was really kind of solidified by our understanding of magnetic fields and by the presence of magnetic fields in rocks at the surface. So magnetic fields can provide us a lot of information about a planet in terms of temporal information, as well as information of hard to reach areas. Okay. Now, just a quick Dynamos 101. Magnetic fields are generated inside planets by dynamo action. Dynamo action is just a way of converting the mechanical energy present in the motions of fluids inside planets into electromagnetic energy. That electromagnetic energy we then manifest as magnetic fields that we can measure. Okay. Now, for a planet to generate a dynamo, and that produces the magnetic field, you need a few required ingredients. Those include relatively complex motions, okay, and that's kind of tried to show in this picture with these really helical-like structure, yellow bands there. Those motions have to be occurring in an electrically conducting fluid. For example, in the Earth, that's the liquid iron core, but in the other planets, the actual material or composition can be quite different. In the giant planets, it's metallic hydrogen. In the ice giants, Uranus and Neptune, it's ionic water, okay? Now, if you have motions in the electrically conducting fluid regions, and there's a presence of a magnetic field, then if these motions act to regenerate the fields more rapidly than the fields decay through ohmic dissipation, then you have what's called a self-sustaining dynamo. So those dynamos end up producing magnetic fields, illustrated here at the surface, okay? And we're going to be visualizing magnetic fields in this talk a lot. And so although this is very pretty, it can actually be a lot of information, and we can show the same sort of information just on the surface of the planet by plotting contours of the some component of the field. So what I've done here is taken the information in these magnetic field lines and just contoured it in terms of the radial magnetic field strength on the surface. So you can see wherever you have lots of field lines coming out, that's contoured by red regions. And so the redder the region, the stronger the field, the more field lines coming out of the planet. Whereas in the blue regions, that's where field lines are coming in. And again, the stronger the blue region, the stronger the number of field lines there. But now the problem is with these lovely 3D models is we can only see half the planet. So when we visualize these, we typically unwrap the planet into a map like this, where we can see the entire surface. So this edge of the plot is the same as this edge. Okay, so this is what this field looks like. So each of the planets, we could produce figures like this to try and start studying what the magnetic field structures are like. And so we're going to play a little game, and I encourage you to use the chat for this. Okay, I'm going to show you a map of the magnetic field for a planet, and you are going to guess what planet it is. Okay, so here we go. So here's our first one. So whose magnetic field is this? And feel free to type in the chat your guess, and guesses are totally fine. Okay, I see one guess. I see lots of guesses. Everyone's saying Earth. Congratulations, you are all correct. That is Earth's magnetic field at the surface. Okay, let's do another one. Who's this? You all are very knowledgeable. Yes, this indeed is Jupiter. Okay, let's try another one. This one might be a little harder. Whose planet magnetic field is this? I see a mention of Saturn, Uranus, Mars. Oh, good. So there's some variety here. This indeed is Uranus. Admittedly, this game gets easier as we go on because we're eliminating planets, right? So you should really guess now because your odds of being right with a random guess are quite good. Who's this? I see Saturn. I see Mars. Saturn, Phobos. Ooh, I like that guess. Mercury, Venus, lots of guesses. This is Mercury. Okay. All right. Who's this? I see Mars. I see Neptune. It is indeed Neptune. Okay. Richard Holm guessed Neptune. That's good, considering he made those maps. Okay. And finally, who is this? I see Mars. I see Saturn. Right. Very few planets left. This indeed is Saturn's magnetic field. Okay. So this game, the intention of that game was really to show you that there is differences between these fields. There's structure there, and starting to try and understand what structure you're seeing here. I should also mention that we could try to find ways to categorize this structure. And what's typically done, or one way to categorize, is by looking at how dipolar the fields are. So what I've marked here in this like purple box are the magnetic fields of the planets that are dominated by their dipole component. So a dipolar field has field lines coming out of one hemisphere and into the other. And you can see for all of these planets, most of one hemisphere is one sign or one color of field, and the other hemisphere is another sign or another color of field. Okay, so these four planets would fall in the dipole dominated category, whereas Uranus and Neptune would fall in the non-dipole dominated, or what we sometimes refer to as multipolar category. Okay, so that's one way to categorize them. There's something else we can look at as well, and that has to do with the symmetry of the field with respect to the rotation axis. So we refer to that as the axisymmetry. And as an example, and I notice it mentioned in the chat, so Mercury and Saturn's field show extreme axisymmetry. So what does that mean? It means if I were to follow along a latitude line or a latitude circle, the field doesn't vary at all. There's no variation with latitude. So Mercury and Saturn seem to be quite axisymmetric. Then you have a second category that I would put Earth and Jupiter in. These fields have good axisymmetry. It's not at the level of Mercury and Saturn, but still, if you were to follow along a latitude circle, your field would pretty much average to something close to what you actually see there, okay? And then there are Uranus and Neptune, and we don't want to say they have bad axisymmetry, so we'll just say they have much less axisymmetry, okay? Here, there's a lot more differences in the field as you as you walk along a latitude line, okay? So this is another way to classify or categorize the field. Now, we should also mention, not to forget that there is also a moon in our solar system that's actively generating a magnetic field. That's Ganymede. We have much less quality of information on what the field is like. So take this image here with a grain of salt. We don't have enough resolution of the data to really see what kind of category this one might fit in, but I include it here. Although it's very frustrating that Ganymede has a magnetic field, because it means that when you make plots like this, you have these two empty spaces here. So I'm requesting that we find 2 more planets that have magnetic fields so that the plots look better. We also can't forget that planets that maybe don't have active magnetic fields or active dynamos today, but they did have active dynamos in their past, and they've left behind remnant crustal fields that we can investigate. And that includes, for example, Earth, which has plenty of crustal fields, but also Mars, who doesn't have an active dynamo today, but does have crustal fields from dynamos past, Earth's moon, as well as Mercury, something that was found quite recently. Now, I should mention, if you really like these figures and you want to make your own, there is a wonderful Python package created by Ankit Barak that you can find at this location, and you can make all these figures for yourselves and use them in your talks. Okay, so I want to, now that we have all of these magnetic fields for these different planets, we want to start trying to do some comparative planetology, right? What do we see when we look at the distribution of, say, length scales for these planets, or even the resolution that we know the field, okay? What you see here on the left is a power spectrum. So you're looking at how much power you have in different components of the field. On the left, I've plotted it as a function of spherical harmonic degree. So the dipole field is at degree 1 here. Then you get the quadrupole, the octopole would at 3, the fourthopole, or whatever that one's called, and you go on, okay? Here on the right is a plot versus spherical harmonic order. This is telling you something about the symmetry of the field. For example, the order equals 0 term here is the axisymmetric component of the field, and the higher orders get contributions from non-axisymmetric fields. So you look at plots like this, and what are you supposed to take out of this? Well, first of all, there's quite a variety in distribution of length scales. Not all of these plots fall on top of each other, right? Some planets seem to have the trend of power as a function of length scale can be quite different from one planet to the other. But there's also a variety in resolution, right? You look here at Neptune, and I kind of cut off Neptune here. And you look at, for example, Earth, which goes all the way down here. This has to do with the quantity and quality of data that we have for these different planets, right? So that's another thing to keep in mind. Another thing to keep in mind that figure didn't show, that was the power of a planet's magnetic field at its surface. But in reality, there is some distance between the surface of the planet and where the dynamo is generated, okay? And it turns out that the power in the field decays more rapidly for smaller scales as you move away from the source distance. So if we really want to investigate the distribution of length scales or the power spectra for a planet, then you want to take the field and you want to look at it at the dynamo surface, not at the planet surface. So here again are the planetary magnetic fields we saw before, and these are plotted at the surface of the planets. But now I'm going to show you this at the surface of their dynamos, okay? So here they are. And so now the game, if I go back and forth a few times, is which planet's magnetic field changes the most when you look at it at the surface compared to the dynamo surface, all right? And so you're looking at these, maybe you're looking at Mercury. Aside from the intensity, the structure doesn't change too much. But then you look at Earth, and I would argue Earth changes the most, okay? Jupiter changes a little bit. The others don't change too much. And this is actually happening because Earth's dynamo surface is actually the furthest away from the planet's surface compared to these other bodies. And so you have farther to go to get down to the dynamo surface, which means that we lose much more of the small scale structure as we observe Earth's field being so far away from it, okay? But there are some warnings we have to put when we do this kind of thing. I took the field at the surface and I downward continued it to whatever the top of the dynamo region is. And in order to do that, you have to assume an insulator between the surface and the dynamo surface. And that's not necessarily accurate. And you also have to assume you know where the dynamo surface is. And that in some cases, that's a little bit easier. For the terrestrial planets, there's sort of a hard boundary between a core and a mantle. But in the giant planets, that's much less well defined. And really, it's about at what depths do the electrical conductivities get high enough that that the flows affect the fields. Okay. But you can do what we did before with the with the surface power spectra, but you can now plot the power spectrum at the tops of their dynamos. And this is what it looks like if you do that. So an important thing to notice here is there's still quite a variety in distributions of length scales, even when plotted at the dynamo surface. So the differences we were seeing before is not just because of differences to depths of the dynamo. However, I find it quite interesting that now that we know Jupiter's magnetic field to much smaller scale or higher resolution because of the Juno mission, Earth's and Jupiter's field plot quite closely, almost overlying each other in this power spectrum here, although there are some differences that we'll talk about, okay? But there's still quite a variety here. And now I have to do my pitch, okay? There's also still a variety in resolution, right? Uranus and Neptune are my favorite planets, although admittedly, whenever I give a talk, I pick some other planet and I say that planet's my favorite planet. And these are the magnetic fields at the surface that are based on models from the Voyager 2 flybys, okay? And you see a lot of structure here, but it should be remembered that all of this structure comes from a single flyby that went across some track across this planet. And most of the structure here that you're seeing is you're seeing because in order to match what was seen across that track, you fit spherical harmonics, and so you get a bunch of information elsewhere. But it's not that we have information everywhere around the planets. And I think this was shown nicely, for example, when work took the same data from Voyager 2, but added a little bit more data. And it was a little bit of unconventional data. It was data from auroral footprints seen afterwards. And you add a little bit more data, and suddenly, so this is Uranus's magnetic field here, and suddenly the field looks like this. So even though, yeah, there are similarities, there's a lot more information or structure here, I should say, than there was before. So this is all to say that it would be really great if we had a whole bunch more data from Uranus and Neptune so we could have more resolved field maps like this. So please send another mission to the ice giants. I would greatly appreciate it. I will buy you coffee forever if you do this. Thank you very much. Okay, so we've been looking at the structure in the fields. We've seen that they have some differences in terms of their distribution of length scales and in terms of the symmetry of the field. And so what I like to do is try and create some sort of classification mapping for this, okay? So I'm going to introduce two axes, okay? The horizontal axis, I'm going to try and plot to discuss essentially the polarity of the field. How dipolar is it? So fields that are very dipolar we'll plot on the left. Fields that are more multipolar we'll plot on the right. On the vertical axis, I'm going to plot symmetry. So fields that are very axisymmetric plot near the top, and the more non-axisymmetric fields plot near the bottom. And I'm very intentionally not putting any quantitative numbers on this plot, okay? But I would put Saturn up here as the most dipolar and the most axisymmetric of all the fields we have in the solar system, okay? Then comes Mercury here. It's also having a lot of axisymmetry, although admittedly our resolution of the data from Mercury is not the same as Saturn, okay? but it's much less dipolar than Saturn's field because of the large quadrupole component in the field. Then I would probably put Earth and Jupiter around here. They're a little bit more dipolar than Mercury, but less exosymmetric. Then Uranus and Neptune are over here, okay? And as all people who love data, what we do when we see data like this is we try and fit a trend to it, and poof, that's what you do, right? So there seems to be some correlation, admittedly with no numbers on this plot, but where dynamos seem to fall for planets in this range. And I think that leads to a question: can dynamos live in these other quadrants, right? We don't have active dynamos that are multipolar but axisymmetric, or that are very dipolar but non-axisymmetric, okay? And I think it's interesting, and this is me kind of going on a limb here, I think that Mars's dynamo may have lived closer to this quadrant, and that the ancient moon even has signs that it may have been in this quadrant, but I think a lot more work needs to be done on that, right? I know there's a curse that says, may you live in interesting times, right? That's supposed to be a curse. I say that we are living in very magnetically interesting times, and that's not a curse, that's a good thing, okay? And I want to point that out. What's magnetically interesting right now is because of the Juno mission at Jupiter and the Cassini mission, which was at Saturn for quite a long time, we now know Jupiter's and Saturn's dynamo fields to a similar spatial resolution as we know Earth's field, okay? The dynamo field. Admittedly, Earth, we know the crustal field's to much higher resolution, but in terms of the dynamo field, we now know these three planets' magnetic fields to similar resolution. And they are fundamentally different, okay? So the differences we're seeing here are not differences in resolution. So why do I think these are fundamentally different? Let's start with Earth. If you look at the small scale features in the field, right, the little blobs, let's say, these things, they're everywhere. So I would categorize this as a magnetic field that has homogeneous small scale structure. Okay, there's no preference for the small scales to be in particular locations. We contrast that with Jupiter, as was shown in a paper by Kimmy Moore and colleagues from the Juno team. Jupiter's small scale structure, basically everything except the dipole, is very concentrated in the northern hemisphere. Okay, so most of the non-dipolar features in Jupiter's field are in the northern hemisphere. And then you contrast that with Saturn. Although it looks dipolar here, there is smaller scale structure in this field. It just happens to be zonal, so it's axisymmetric. So again, small scales are present here, but they are zonal in structure, not homogeneous, and not even hemispherical like this. So there seem to be some fundamental differences in these three planetary dynamos whose fields we kind of know to similar resolution. Now I'm going to make a scary claim, and we're close enough to Halloween that I'm allowed to make scary claims here, okay? These differences that we see, I'm going to claim, are not due to different parameter regimes. So when we study planetary magnetic fields in the dynamos, there are all sorts of governing non-dimensional parameters or important combinations of parameters that give us information about how the field should behave. And for example, there are these fabulous scaling laws, which tells you whether or not to expect your dynamo to produce a dipolar field or a multipolar field and things like that. But these smaller differences here, I'm going to claim, or my feeling is, these aren't due to differences in major parameter values, right? It's not because the rotation rates of these planets are different, or not because the material properties are somewhat different, okay? Now, why is that scary? That means we can't use scaling laws to predict these field features, okay? Or at least the scaling laws we've thought of up until now, all right? But I think it's also good news. I also like Halloween, so this is okay. I think this is good news because I think this says that there's real, let's say, opportunity in the details here. Those small scale features tell you something about complexities of the dynamo region, okay? And what kind of complexities could we be talking about? And I've just listed some here that have been proposed for a variety of different dynamo regions in planets, right? You might have stably stratified layers, exotic material phases, strange thermal perturbations at different locations, density stratification, regions that are intermittent conductivity with overlying higher conductivity. Even now you hear phrases such as fuzzy cores when talking about Jupiter's interior, okay? And you can take these types of details and you can even kind of place which ones you think might be applicable to variety of planets. And, there's a lot of things here, right? So studying these small scale features, which we are starting to be able to do because of the quantity and quality of data, may help us learn a lot of really interesting things about the deep interiors of these planets that are really hard to learn in any other way. Okay, so how do we investigate this? Ultimately, we try and test these complexities with Dynamo simulations, okay? And for those of you who don't do this on a regular basis, what we're ultimately interested in is how do things like the fluid velocity, the magnetic field, the energy fields here represented by temperature, how do they behave, okay? That means figuring out the equations that govern these variables. And for us, that's something like a momentum equation, a magnetic induction equation, and an energy equation. Then you got to work in a particular geometry, apply your boundary conditions. Then the equations are too hard to solve, so you make approximations and hope they're okay. But ultimately, you evolve this system in time. And as output, you get the magnetic velocity and energy fields later on. And you put those back in as your input, and you evolve this in time, okay? Just talking quickly about the geodynamo, okay? This is the kind of thing that we're trying to have models reproduce, okay? So on the left here is a observational model of Earth's magnetic field changes since the 1600s, okay? So you can see that we have the field structure for over 400 years, but we also have information on the time variation of the field, okay? On the right is a spectrum of the temporal behavior of Earth's dynamo that we get from information like these movies of the field structure, but also from paleomagnetic studies of how the magnetic field has changed in the past, right? So you can see at very long time scales or very low frequencies, you have reversals, then there are other sorts of temporal variations that you can see from a power spectrum like this. So that's Earth. We live here. We get lots of data about Earth. To a planetary scientist, someone who's interested in understanding perhaps some other planets' magnetic fields, this range and detail of information are exquisite, and we have no hope really in the near future of having anything like this in order to investigate the types of things we can investigate by studying Earth's magnetic field. But that doesn't mean we can't learn anything about planets. Although we would love to have a fancy frequency spectrum plot, because it's not feasible in the near future, we're going to concentrate on the things that we can try to understand. So what does that include? Let's think of some big questions that might be of interest for other planets' magnetic fields. First of all, the timing. When was the dynamo active on that planet? How long has the dynamo been active on the planet? That really tells you important information about the thermal history of the planet. Did the dynamo have reversals for other planets, right? That tells you something about the dynamics of the dynamo region, the fluid motions in that region, okay? Is there time variation of the field, kind of faster time variation than, say, a reversal? So just moving around a field parcels. These are the types of questions that we can get at now, or start getting at perhaps with the data that we have, okay? So let's start by thinking about dynamo timing. So this is going to be a plot where here's the time axis. Today is at 0, back to 4.5 billion years ago. And we're going to look at each of the bodies in the solar system for which we have magnetic information, okay? And you can make plots like this. So for Mercury, for example, we know that Mercury has a dynamo today, okay? And that's shown by a solid colored in region here, okay? Messenger also showed us that Mercury has crustal fields, implying a dynamo early in its history between about 3.9 and 3.7 billion years ago. In between, well, we don't really have any data that tell us whether or not there's a dynamo active at this time, but there's not a good reason to suggest to think about why there wouldn't be. So I've kind of put that as a hatched region, that yeah, there could have been a dynamo, but we don't actually have data on that, okay? Move on to the next planet. Here's Venus. All we know about Venus is it does not have a dynamo today, okay? Did it have one in the past? Well, if you look at potential thermal evolution models for Venus, it's possible that it had one in the past, but we do not have data to confirm that. Then you look at someone like Earth, some planet like Earth, right? We know it has a dynamo today. Oops, I went too fast. We know it has a dynamo today. We know because of paleomagnetic studies that it's had a dynamo for most of its history, okay? Again, gets a little bit harder to discern earlier in its history. The moon. So the moon, based on lunar magnetism studies, demonstrates that it did have a dynamo in its early history and may have had one up until, and this can extend now depending on the latest analysis of lunar samples and their how much magnetic field one can infer from those lunar samples. But the moon had a dynamo in its early history, but it does not have one today. Okay. Mars, we know it doesn't have one today. It did in its early history, again, from crustal rocks on Mars. And recent papers show that there's even possibly a second epoch of dynamo action a little bit later on. And we don't really know what was going on before or after. Jupiter definitely has a dynamo today, and we have no reason for it would be very hard to create a model where Jupiter didn't have a dynamo throughout its history. Okay. Ganymede, all we know is, yep, today, no idea about the past. With the giant planets, you get the same story as Jupiter. Yes, they have dynamos today. It's very hard to see how they wouldn't have had them for their full histories. Okay. But there's also small bodies, things like asteroids, planetesimals in the early solar system. Work has shown that these bodies can actually have had dynamos in their early history, but they have to die out very young. Okay, so that's timing. Now let's talk about reversals. Okay, and here we have to get even more. This is where we go to the emoji bits of the talk. Okay, so does Earth have reversals? Yes. Okay. Other planets? We don't know. Okay. It's very hard unless you happen to be capturing a planet in the middle of reversal, or you happen to have enough paleomagnetic data in the rocks on the surface of a planet. So this requires the planet has a surface of rocks. It's very hard to know whether or not they had reversals. Okay. There has been work on lunar crustal rocks and Martian crustal rocks where you infer from specific crustal anomalies or magnetic fields in the crust whether or not the pole of the dynamo that produced those crustal anomalies has changed in time. So there is some work out there suggesting that there is evidence that the moon's dynamo had reversals and that the Martian dynamo had reversals, but this is controversial. Okay. What about temporal variations that aren't reversals? Okay. Again, for Earth, yep, we have data, even present day data, showing how the field changes in time on sort of smaller time scales, right? What about other planets? Well, if you're a fan of the lunar paleopole and Martian paleopole studies, then yes, there's also information there that suggests that the fields changed on shorter time scales as well, okay? But here now we can actually start talking about even Jupiter because of the Juno data itself, and then even comparing back to the earlier data from other missions, okay? However, the time variations we're seeing here appear that they might actually be due to strong zonal winds that are in the outer layers of Jupiter. So we might not be actually capturing the dynamo region in motion, changing things. It may be more of just advection of field features we see in the outer layers, okay? Saturn, there has not been any variation in the field strongly detected, let's say, okay? And this was done early on in the Cassini mission, work by Hao Cao, and then even more recently now, work by Kimmy Moore and colleagues. There has been no temporal variation of the field detected over the decades that we've had data. But that might be expected, actually, because there are some other enigmatic features of Saturn's magnetic field. And if you have to try to explain those, it turns out that it's likely that you do not capture any temporal variations of the field outside of the dynamo region, okay? All right, so now I want to turn to a case study. You know, if we had forever here, I would talk about every single planet in lots of details, but I decided to just pick one and tell you kind of the story of how we've used magnetic fields for this planet to really learn about its interior, okay? And the case study I'm going to pick is Mercury. And Mercury was first visited by spacecraft by Mariner 10 in the mid-70s, and it took magnetic data, and it demonstrated that Mercury has an active dynamo. And this was not expected beforehand. Mercury is a small body. People thought that, well, we know that small bodies cool faster, and so we're not expecting there to be a liquid core in the planet that could generate a dynamo. But voila, it did. Okay, so that was the first thing. This confirmed that, yeah, there was a liquid core in Mercury. And suddenly then we had to kind of think in terms of thermal evolution and composition implications for that. And indeed, it worked out, right? People figured out that if the iron in the core was mixed in with a little bit of some, what do you call those? A material that could raise the freezing point, then you raise lower, that could change the melting point, basically, then you could keep the core liquid up until present day, okay? The Mariner 10 mission also demonstrated that the field is very weak in intensity, okay? And that actually became problematic initially in terms of trying to figure out how a dynamo could produce a field that's so weak, okay? That turns out that if you generate a dynamo, there are ways you could estimate how strong the field should be. And Mercury's field seemed to be too weak, okay? But that's okay. There were a bunch of researchers out there. I was involved in this too. We all came up with mechanisms that could create a magnetic field that was nice and weak to explain Mercury's magnetic field, okay? And you don't have to understand the details in these models, but what you should be seeing is there are a variety of different strange things that we could do with the core region. So these are meant to represent the cores of Mercury, and these are the convection rolls, and you can see all sorts of things like stably stratified layer, thin convective layers, double layer stratification due to iron snow, small inner cores, right? There was all sorts of stuff suggested, and all of these models could reproduce the weakness that Mercury's magnetic field showed. And all of these models made predictions for what other features to expect for Mercury's magnetic field. Now, we didn't have data on some of those other features at the time, but we knew that Messenger was going to Mercury and was going to give us all sorts of new information, right? So then Messenger arrived at Mercury, and it confirmed the weak field strength that we knew from the Mariner 10 mission, okay? But it also showed, based on the data, that, for example, the dipole is very exosymmetric, okay? So that's a new structure of the field that we want to explain. It also demonstrated that the dipole has a significant northward offset, which is equivalent to having a large quadrupole component of the field, okay? So then the question became, can a dynamo reproduce all of these observations, okay? So you look back at the old models that had been put forward to try and explain the Mariner 10 data and hope to be confirmed by by Messenger data, right? And you end up with this sort of scenario, right? We're thinking about it. We thought we had good ideas. Then we got data, and now we're here. Okay, so this is the fate of all theorists, is that you come up with a great idea, and then new data shows you that it was wrong. Okay. Another thing that Messenger showed us, which was really important, was the crustal fields. Right, the planet has had a dynamo for a long time that fundamentally constrains properties of the interior, okay? So since we have the Messenger data with this new structure that we want to explain, there have been new contestants that have been put forward to try and explain the field structures. And here's one of them. This was work by Hal Cow and colleagues. And the idea here was if you drove the dynamo, so the core of Mercury is quite large, right? It's a very large fraction of the planet. If you drove the dynamo with internal heating here and you put some thermal variations on the top of the dynamo represented here, then you could produce a magnetic field that had that dipole offset that we saw before. Okay, so it was able to do that, and then it produces a fairly exosymmetric field as well. This model's the challenge for this model is that the field it produces is a little bit too strong to be consistent with Mercury's field, but it's one idea showing you that adding these small complexities can actually help you in trying to reproduce the fields that we see. And here's another contestant. This was work that I was involved in. It also had the dynamo region, but it had it surrounded by a stratified region, which had been suggested in the past by people like Uli Christensen and others, based on the understanding of the heat coming out of the planet. Okay, but here we did something a little bit different. We put a different pattern of thermal variations on the top of the region, okay? And that did produce a magnetic field that, again, gives you the offset, gives you the axisymmetry of the field, and can give you the weakness of the field. But the sort of the hard question for this one is why on Earth would the planet have this kind of thermal variation at its surface? So that's what this one has to try and answer, okay? Then there was another contestant more recently, work by Takahashi and colleagues, that again used a stratified region, but really tried to take into account the fact that there could be, there are buoyancy sources in the dynamo that could be thermal in origin as well as compositional in origin, and you can get all sorts of interesting behavior if you consider double diffusive convection. And they were actually able to produce a model that had all those signatures again: offset, axisymmetry, weakness of the field. The big question here, I think, was that this worked for a very specific grouping of parameters. And if we start changing those parameters and thinking about what the parameters should be for the real planet, will this still work? Okay, so those are the open questions at the moment. Now, the good news is that there's hope for new data, right? So we're very excited that Bepi Colombo is the mission that will be bringing us the latest data from Mercury in the future. And in fact, Bepi Colombo just finished its first flyby of Mercury this a couple of weeks ago, I guess 3 weeks ago. And there are planned future flybys. Again, you have to fly by a planet several times in order to slow it down to put it in orbit, especially when trying to go into the inner solar system. And so Bepi Colombo will get to orbit in Mercury in late 2025. And so there's hope for new magnetic data. And the question will be then, will we again be in that scenario where the Bepi Colombo data leans over our shoulder and tells us no to all of our ideas, or what will we learn about the magnetic field? But I think there's also hope, and there's other prospects for getting more data from Mercury, okay? And you can think about this the most when you start, when you look at what is the challenge in getting good magnetic data from Mercury. And the biggest challenge at Mercury, I would argue, are the external fields, okay? Mercury is very close to the sun, the solar wind is strong there, plus the field is very weak, which means that the magnetosphere is very small. So there are lots of external fields that are present in the data when you're trying to collect data while orbiting the planet. So I think there's a lot of work going on, and this might actually produce a lot of new information. If we can figure out how to better characterize the environment of Mercury, the magnetospheric fields, through simulations, through other data from that, then we might be able to better subtract those fields from the data that we have from MESSENGER and really take that data and learn more about the interior of the planet. And we've been seeing this even today. So this is work by Dong and colleagues, but there's also recent work that came out by Alain Plattner and colleagues looking at once you start modeling these external fields, you can start seeing smaller scale features in Mercury's magnetic field. And so there's some interesting dynamo structures that people are seeing nowadays. All right, so just to summarize here quickly, what I'm trying to convey here is that planetary magnetic fields, they all have their own peculiarities, okay? So we have to be a little bit careful when we try to apply sort of simple scaling laws to them, right? Maybe scaling laws work for things like, should a planet have a dynamo? Or is that dynamo dipolar? But we're getting the level of data nowadays that we can ask harder questions, and those answers to those harder questions might involve complexities in the dynamo region that are much harder to explain through simple scaling laws. But because of that, we can use those peculiarities to really learn about the interior structure and dynamics of planets. And so there is a major opportunity here. Magnetic fields are a really powerful tool to observe a planet's interior. And as many people know, that's kind of hard to do, okay? And with that, I will say thank you, and I'm happy to take any questions.
Thank you very much, Sabine, for this fascinating talk, and didactically very, very good, very well prepared. I think you were the first to, ask questions to the audience during the talk, at least in the Game Changers seminar. Very, very well done. Thank you very much. So we have two ways of posing questions. I mean, you can raise your hand and and then Willie will give the floor to you, or you write a question in the chat, and so that everybody can hear the question. I will then read the question to Sabine, and she will answer. So at the moment we don't have a question in the chat, so I give the floor to William Wall to ask the question. Willie, can you open the mic for William?
Yeah, hello. Yeah, I love your talk. It's beautifully organized and beautiful figures too. Yeah, I was wondering about, I'd read that the sun's magnetic field played an important role in the formation of the planets, which in turn would affect the kinds of magnetic fields that those planets would have. So could this allow us to infer some certain insights into the sun itself? I'd love to hear your comments on this.
Yeah, thanks. So yeah, so the sun does have its own magnetic field, and that creates the solar wind, and it distributes magnetic fields throughout the solar system. I don't think it's well understood or necessary that the sun's magnetic field was required for planets to produce the magnetic fields, except maybe the fact that you need to have a seed magnetic field in order to get a dynamo generated. But there are other ways to get seed magnetic fields. So I would argue it's not the case that the sun's magnetic field is required to produce or even strongly affects any planet's magnetic fields. The sun's magnetic field can interact with planetary magnetic fields, and that's what creates the magnetospheres that surround the planets. And indeed, processes there can affect, for example, observations we make or things like that. But except for maybe Mercury, where the magnetosphere is so small that the solar wind can almost directly interact with the core, I think other planets, it's not such a big issue.
Okay, it's just that I'd read that it can affect the sizes of the cores of the planets when they're formed, that they have, let's say, a large metallic core. For Mercury has a larger core.
Yeah, there was a recent paper that came out actually that suggested a relationship between the core size and distance from the sun. Interesting. So I remember thinking when I read that actually the latest data from InSight, the InSight mission at Mars that determined the core size on Mars, suggests that the Mars core is a little bit on the large side from what we figured. And it actually, if I remember correctly, it kind of ruins that scaling law that came up. So it might be more complicated than that. And really, especially with Mercury, if the big question is, did Mercury, is the large size of Mercury's core due to sort of just the general characteristics of where it formed, or was there a giant impact that removed a bunch of mantle, in which case, again, you have to be careful with any sort of scaling of core size.
Right, thanks.
Okay, the first question, there are questions in the chat now. The first is by Andrew Coates, and he asked, where would the sun fit on your symmetry diagram? Bottom right?
That's a great question. Okay, so the sun's magnetic fields, where would it fit? So I would say that the sun's magnetic field kind of has two components. On the largest scale, it's got this very weak dipolar field, which would put it kind of in the dipolar axisymmetric part. So the large scale structure of the sun's field, the part that we kind of gets out to the planets even through the solar wind and things like that, that's axisymmetric dipolar. But there are also very strong, intense, small scale structures in the sun's magnetic field that result in sunspots that we can even detect. And those fields are incredibly intense, incredibly small scale, so incredibly multipolar and very non-axisymmetric. So there's almost, for the sun, there's two components to the field. There's the weak dipolar field that's much more stable, stays there forever, and then there's the small scale structures. And that's probably a result of the fact that there are different processes generating those two components of the field. They do interact, but that's where I would put the sun.
Okay, John Sunecki. Hi, John. Asks, what do we know about exoplanet magnetic fields, if anything?
Oh, yes, this is exciting. So lots of people are looking for exoplanet magnetic fields, and there are a variety of ways you can do this. The most direct way we want to be able to do this is by, for example, detecting radio emissions that might result from electrons spiraling along magnetic field lines in polar regions of a magnetic field. So that's, for example, how we detected Jupiter's magnetic field back in the 50s, right? So that's sort of the gold standard of what we would like for exoplanet magnetic fields. That's really hard to do because the strength of the radio emissions depends on a variety of factors, including how strong the planet's magnetic field is, how far away it is, things like this. Right now, we're kind of on the edge of ability to detect such fields based on the radio telescopes, I guess it's radio antenna we have, the systems we have to study them. There are more indirect ways to see an exoplanet's magnetic field, and that can happen, for example, by emissions of basically energy emissions, or looking at spectral features that are actually happen on the star, that are caused when magnetic field lines from a planet may interact with a star's magnetic field. So people have seen spectral signatures in stellar emissions that suggest there might be magnetic field interactions between a planet and a star. And there have also been some studies in, I think it's like the UV wavelength range, that show evidence for a region surrounding a planet like a magnetosphere. And so there are these indirect detections of magnetic fields of exoplanets, and I think more data is needed. I think a lot of them are still kind of, we need more data to confirm sort of phase, but there is data like that. But I think it will be really exciting once we get more of the direct observations.
Okay, Dibiyendu Nandi, I hope I pronounced that somewhere correctly. Is there any understanding when the Earth might lose its dynamo or the temperature gradient to drive convection, that drives convection?
Yeah, that's a good question. So I think this really, again, is something that depends on the details of the dynamo region. When people have been trying to understand the energetics of the dynamo, how much power is there to drive Earth's dynamo? Perhaps a little bit of a scary answer to the question is not much. There's not much power. And in fact, sometimes it's challenging even to understand why Earth has a dynamo active right now. So I think it's hard to answer the question of how long the dynamo will last, because it really depends on some of those fundamental things like the exact composition of the core, sources of buoyancy in the core. And so that's a hard question to answer. But it's been around for at least 4 billion years ago, maybe even, or 4 billion years so far, maybe it'll be long for a while. So it might be a little bit unique if we happen to be living at the time that it's going to decay away. There are no signatures, let's say, in the strength of the field that we've seen over the past few billion years, suggesting that something fundamentally different is happening with the field now. So it does seem to be fairly stable, whatever it's doing.
Okay, Jerome Bouvier asks, is it possible to somehow extrapolate these results to guess the magnetic field of giant planets at the time of their formation, when they are still embedded in the protoplanetary nebula? It has about 1 billion years after formations.
That's a great question. And I'm actually really interested in trying to understand what goes on while these giant planets form. I think what you can do is use sort of the standard scaling laws for when would you expect the fluid motions, when would you expect a planet to be giving off enough heat, cooling fast enough, let's say, so that it can generate a dynamo. In order to do that, you need to know some information about the composition and the thermal structure of the planet. And from that, you could say, yeah, it's likely that this planet had a magnetic field at that time. And you might be able to use simple scaling laws if you assume that the fields were dipolar, for example, to figure out the intensity of the field. It depends a lot on the details, but I think if you know enough about the thermal behavior of the body, then you could do that sort of thing.
Okay, Suvik Roy, nice talk. And then the question, is there a relation between planetary magnetic fields and its atmosphere? And later, he or she asks, and chances of habitability in case of exoplanets. So relation between magnetic field, atmosphere, and habitability, basically.
Okay, so Suvik, if you are a fund program manager that I'm going to ask for money from, then my answer is going to be yes. We think there might be, right? No, so that was a little bit of a joke, but the short answer is we don't know. Okay, there are interactions we know of between how strong a planet's magnetic field is and how much atmosphere, for example, can escape from a planet based on its magnetic field, but we don't even know the sign of that interaction. For example, if you have a strong magnetic field, does that mean you lose atmosphere faster or slower than if you have no magnetic field? And it can really depend on the details. And the MAVEN mission at Mars right now has been really instrumental, I think, in trying to get to those answers to those questions. So there are probably relationships and implications for a planet's atmosphere if it has a magnetic field, but it's really hard to understand what those are. And it's harder, I would argue, the bigger the planet is. So let's take, for example, Earth. You see Earth, and we know we have a great atmosphere conducive to habitability, and we know we have a strong magnetic field. So you're like, okay, maybe there's some sort of relationship that good magnetic field equals lots of atmosphere. But then you go to Venus right next door, tons of atmosphere, no magnetic field, right? So it's not straightforward. And I think a lot of people are working on that problem.
Another interesting one here. In the case of Mercury, how much is the problem degenerate? In other words, do you expect that having access to more and more spherical harmonics could, for instance, help reducing the internal structure and or physics possibilities?
Yeah, the more data, the better, right? The more data we have, the more things we can eliminate as possibilities. But I should also mention, and this is true for all the planets, but also true for Mercury, we usually don't use magnetic fields alone to understand planetary interior structure, right? There's a variety of other methods or observations that we can use to constrain the interior of a planet. Things like the gravity field of the planet, things like the rotational dynamics of a planet. All of that comes together to give us a vision of what the interiors of the planets have to be like. So it's really about, I think, the power is in having that combination of data to understand what's possible for planetary interiors.
Okay, Karen Molla-Verdicani asks, how would tidal forces affect the interior magnetic field of, for instance, Mercury, Io, or packed exoplanets like TRAPPIST, the TRAPPIST-1 system?
Yeah, this is a good question. And some people who study dynamos are looking at things like tidal forces or even other mechanical driving forces. So anything that could kind of cause flows in the cores of these bodies might produce magnetic fields, right? And so there are people who are looking at the impact of tidal forces on a planet like Mercury. So the short answer is it's possible, but we're still working on the details, and it's actually a hard problem. The flows you generate from tidal forces or precessional forces, for example, is another one that people mention. The flows you generate from that are either really simple, and then they're hard to generate dynamos, or they're really complex, and it's really hard to simulate and predict. So the work right now going on by several people in the community is to try and figure out what are the flows that are generated by tidal forces and precessional forces and other things like this, impact forces. That's another one that's mentioned for dynamos. And if you have a big impact on a planet, you can suddenly torque it, and can that generate flows that would generate a dynamo? So there's a lot of active research going on in understanding the fluid dynamics of that, what instabilities you generate, how much turbulence can you generate.
Okay, and then why Saturn has a highly exosymmetric dipolar field.
I gave a talk yesterday about that. Yeah, so I gave a talk about that yesterday. So Saturn's, the shorter answer is we have some ideas. We don't know for sure. The axisymmetry of Saturn's magnetic field is really problematic for dynamo theory in the sense that it's really hard either with simulations or with theory to figure out how you would produce a field that's so axisymmetric like that. But there have been ideas out in the literature since the early 1980s, late 1970s, first, I think, led by Dave Stevenson, where if you have a mechanism that can take a field that's not axisymmetric in the dynamo region and then make it, shear it out, make it look axisymmetric by the time you get to the surface, then we're fine. And for Saturn, that mechanism might be something called a helium insolubility layer or helium rain that we think occurs inside the planet. So basically the dynamo of Saturn is surrounded by a stably stratified electrical conductor, and through an electromagnetic skin effect, it can shear out all the non-axisymmetric features. So my group has been running simulations to try and understand that. There's been work by Chi Yan as a postdoc in my group, formerly a grad student, and her work was really on that. And we had a paper about that earlier this year. So we think that the axisymmetry might be due to an electromagnetic skin effect, basically shielding us from the non-axisymmetric features deeper in Saturn.
Thank you very much. I think we exhausted all the questions in the chat. We let you run off to your next meeting. Thank you very much, Sabine, for spending the time with us. I just wanted to announce that next week, we're having another astrophysics seminar of bubbles, filaments, echoes, and eruptions. First results from the eRosita mission by Andrea Meloni from the Max Planck Institute for Extraterrestrial Physics in Garching in Germany. And with that, I would like to close this week's seminar. Please note that the seminar has been recorded. So if you want to look at it a little closer, then you can download that or use YouTube to listen to Sabine again. Thank you very much, Sabine, and have a good day. And thank you very much to you listening to us, and see you next time. Okay, bye-bye.
Thanks, everyone.